Alrighty. So this is the last sort of sub-lesson in the unit of dynamics. And it basically deals with equilibrium. I have two handouts. One is more sort of instructive and descriptive. You want to use scientific terms, a little more qualitative. And the second one gets into the problems and becomes a little bit more quantitative. So here, let's begin. In the absence of force, objects stay at rest, and objects in motion continue motion. You know that from grade 10, grade 11 as well, Newton's law. More specifically, in the absence of a net force, objects do not change their state of motion. For example, if you push with equal and opposite forces on opposite sides of an object at rest, it will remain at rest. The forces cancel each other out, and there is no net force, or the net force would be zero. The combination of all forces acting on an object is called the net force. It is the net force that changes an object's state of motion. Figure 410 shows how forces combine to produce a net force, and you guys know all this. This is nothing too surprising. I think I'm just going to skip all that, right? I think it's pretty straightforward. Let's go right to 4.7. Equilibrium when the net force equals zero. What forces act on your book while it's motionless on a table? Don't just say its weight. If only the force of gravity were acting on the book, it would be in free fall. The fact that the book is at rest is evidence that another force must be acting on it. This other force exactly balances the book's weight and produces the net force of zero. The other force is the support force of the table. Support force is often called the normal force, and you guys, we've been talking about that for a while, right? That's no big surprise. As shown in figure 411, the table pushes up on the book with a force equal to the book's weight. When an object is at rest, the net force on it being zero, we say the object is in a state of equilibrium. Okay, there's a key term there. Equilibrium means the net force is zero. Does the table really push up on the book? Yes, just as the spring pushes up on your hand when you compress it. Look at figure 411, you can feel the spring pushing back on your hand. Similarly, a book lying on a table compresses the atoms in the table. Behaving like microscopic springs, the atoms in contact with the book push back on it. Since the book is in equilibrium, the net force on it must be zero. The table actually pushes up on the book with the same force that the book presses down. An ant trapped between the book and the table would feel itself being squashed from both sides, the top and the bottom. When you hang from a rope, the atoms in the rope are not compressed. Instead, the atoms are stretched apart. A tension force is established in the rope, and a rope under tension will twang like a guitar string if you pluck it. How much tension is in the rope when you hang from it? If you are in equilibrium, then the tension must equal your weight. If the rope pulls you up and the force of gravity pulls you down. Since the equal and opposite forces cancel each other out, you hang motionless. So that's just sort of an introduction kind of review of where we're headed here, right? Suppose you hang from a bar supported by two ropes, as in figure 412. Neglecting the weight of the bar, the tension in each rope is 1/2 your weight. So here they have the kid, right? Whatever weight they have, like let's say the kid weighs, oh, I don't know, we'll say 25 kilos times 10. Let's say the kid weighs 250 newtons. Well, then you'd have 125 there and 125 there, right? The total tension force acting upward, 1/2 your weight plus 1/2 your weight, balances your weight, which acts downward. When you're doing pull-ups using both arms, each arm supports 1/2 of your weight. Have you ever tried pull-ups with just one arm? How many people can do it? Not very many, right? You just don't have the same strength to weight ratio. That's why you need both. A spring scale can also be used to measure tension. When we weigh a bag of apples by suspending it on a spring, the scale reading tells us the weight. Consider a 1 kilogram bag of 10 apples weighing 10 newtons. When suspended by a single vertical scale, as shown on the left in figure 413, so that's this one down here, the scale reads 10 newtons. So there's my bag of apples. It weighs 1 kilogram, which is 10 newtons. 10 newtons down, there's 10 newtons of tension in the string, and the scale will show it. And I'll pull the scales out right away, I guess. Should have had those out. If instead we hang the 10 newton bag from a pair of vertical scales as shown on the right in figure 413, each scale reads 5 newtons. The two scales pull up with a combined force equaling the bag's weight. Since the bag hangs at rest, the net force on it must be zero. The key concept is this: if a 10 newton bag is in equilibrium, the resultant of the forces applied by the pair of springs must equal 10. If the spring scales are oriented vertically, straight up and down, this is easy. 5 plus 5 is equal to 10. So moving on. Let's now consider non-vertically oriented spring scales. The tension is greater in a pair of non-vertical spring scales and depends on their angle from vertical. This more complicated situation is most easily understood using vectors. So hooray for vectors again, right?
Yay!
More vector addition and subtraction.
Woo!
Recall our treatment of velocity vectors in Chapter 3. We'll now use the same vector addition techniques with forces. Force, like velocity, has magnitude and direction and is a vector quantity. Look at the left of figure 414. Notice that when the spring scales hang at 60 degrees from the vertical, their readings are 10 newtons each. Double the tension of the vertically hanging scales. So when you do this, right here, if I've got 10 newtons down, usually I should have like 5 and 5 of it straight up, right? But here I've got it at an angle. That's 10. That's also 10, which is a total of 20, which is more than what is down. Why does that happen when you go sideways like that? I'm hesitant to do that with this because A, I think it's going to break and B, my back is going to sore. But if someone wants to come and volunteer, do it. I need someone long arm. Well, come on. We'll take the call. He's a long arm. You're just going to lift that up, and then you're going to hold this up like this.
Yeah, so not your attention span.
I want you to stand this way so they can see it. Okay? So, now you don't, it will, I've had the string snap before, so don't hit your head. Okay. So what do the scales say now? Can't see them? Centers? That one's about 7. Is that one about 7 from the scale? 7 or 8, something like that. Okay, so now put your arms as wide as you can, Blaine. You'll see that, right? Can he get the wire straight? Can you get it flat? Even if he had longer arms, he could. Right? And we're maxed right out like that, right? Okay. Easy man. Don't want to lose an eye. I actually usually wear safety glasses when I do it. One time I did get smacked in the head. Whatever. I wasn't too early. Yeah. For an angle here, where am I here? Because the sum of the two tension vectors must support the downward acting 10 newtons. Wait, the sum of the vectors must be 10 newtons, directed vertically upward as shown by the diagonal of the parallelogram formed from the two vectors. For an angle of 60 degrees in the vertical or 120 between the scales, 10 newtons of tension force is required in each scale. For angles greater than 60 degrees, the scale readings would increase even more. Notice on the right of figure 414, this one down here, the angle from the vertical is increased to 75.5. So this is a huge angle here. That's going to be like 160 degrees. At this angle, each spring must pull with 20 newtons to produce the required 10 newton vertically upward result. As the angle between the scale increases, the tension in the scales must increase for the resultant to remain 10 newtons. In terms of the parallelogram, as the scale's angle from the vertical increases, the magnitude of the tension force must also increase for the diagonal to remain the same. So what's going on here? Okay, if you've got, I'm going to look at this picture here, get rid of that blue there. If you've got 10 newtons down, you have to have a total of 10 newtons up. But because this is at such an angle, like that, right, there is this component, right? So we'll call this one T1, and we'll call this one T2. That should be capitals. T1 and tension 1 and tension 2. What would you call this part right here? T2y, the y component. And this one over here would be T1y, right? And so what you get is T1y plus T2y have to add up to 10. In other words, they're both equal to 5, right? But because of that huge angle, 75.5 degrees in there, to make 5 straight up and down, this value here has to be 20. And as that angle increases, right, you need more and more tension to create that 5 newtons upward. Does that make sense? Awesome. If you understand this, you understand why a vertical clothesline can support your weight, but a horizontal clothesline cannot. The tension in the nearly horizontal clothesline is much greater than the tension in the vertical clothesline, and therefore it breaks. For any pair of scales, ropes, or wires supporting a load, the greater their angle from the vertical, the larger the tension force in them. The resultant of the tension forces, or the diagonal of the parallelogram they describe, must be equal and opposite to the load being supported. As you'll see when you answer the following questions, the parallelogram technique of adding vectors yields some very interesting results. Okay, so yeah, This, no problem. This, not so good, right? Why? Because of that angle thing again. So here's a question. When you step on a bathroom scale, the downward force supplied by your feet and the upward force supplied by the floor compress a calibrated spring. The compression of the spring gives you your weight. In effect, the scale measures the floor's support force. What will each scale read if you stand on two scales with your weight divided equally between them? So you've got two bathroom scales that are really thick for some reason, and here's a really weird looking stick person, right? And let's say they have a mass of 180 pounds, we'll say. So each scale would say what? Each scale would say 90, right? So if you want to lose weight, just get another scale. It's easy. What about this one right here? If the children on the swings are of equal weight, which swing is more likely to break? A or B? Which one is more likely to break? B would have more tension. B would have considerable more tension. Consider what would happen if you suspend a 10 Newton object midway along a very tight horizontally stretched guitar string. So you've got two stands, some kind of metal stands, like so, and you've got a guitar string tied between them. Is it possible for the string to remain horizontal without a slight sag at the point of suspension? Can you get that perfectly straight? The answer is no, because even a very thin G string on a guitar would still have a little bit of weight, right? And so there would be a little bit of mass, and so in fact it would actually look like this. And I'm exaggerating for effect, right? But it would look like that. In fact, it would hang in an arch like that. If you take a chain and just hang it, it forms that sort of shape, you know? It's not a parabola, by the way, it's like a tenorary arch, which I will show you more about right away. Oh, where is it? Had some good links. Alrighty, so let's look at some more quantitative stuff here, equilibrium. You already know one example of force in two dimensions. When friction acts between two surfaces, you must take into account both the friction force that is parallel to the surface and the normal force that's perpendicular to it. So far, you've considered only motion on the surface. Now you use your skill in adding vectors to analyze two situations in which the forces on an object are at angles other than 90 degrees. Here's a key term, equilibrium and the equilibrant. There's a new word for it. An object is in equilibrium when the net force on it is zero. When in equilibrium, an object is motionless or moves with constant velocity. That's key as well. That's a concept from grade 11. According to Newton's laws, the object will not be accelerated because there is no net force on it. You've already added two force vectors to find the net force is zero. Equilibrium also occurs when the resultant of three or more forces equals a net force of zero. Figure 1a shows three forces exerted on a point object. What is the sum of A, B, and C? Or what is the net force on the object? Remember that vectors may be moved if you don't change their direction, angle, or length. So as we did in grade 11, I demonstrated here. I'm going to go three different colors. There's red, blue for B, black for C. And if you add them up, right, there's A, there's B, and there's C. Where do you end up? Right back where you started. So the net force here is zero. They are said to be in equilibrium. Figure 1b shows the addition of the three forces, A, B, and C. Note that the three vectors form a closed triangle. There's no net force, so the sum is zero, and the object is in equilibrium. Suppose only two forces are exerted on an object, and the sum is not zero. How could you find a third force that, when added to the other two, would add up to zero? Such a force, one that produces equilibrium, is called the equilibrant. So in this case here, if you've got forces A and B, if you know A and B, then C is the equilibrant. Okay, so the equilibrant is the force that produces equilibrium. Okay? To find the equilibrant, first find the sum of the two forces exerted on the object. The sum is the resultant force, R, the single force that would produce the same effect as the two individual forces added together. The equilibrant is thus a force with a magnitude equal to the resultant, but in the opposite direction. That is one of the key terms from today. The equilibrant is equal to the resultant, but in the opposite direction. In fact,
E is equal to minus R. E is equal to minus R. Figure 2 illustrates this procedure for two vectors, but any number of vectors can be used. So there's A and B. You put them tip to tail. A, B. Draw your resultant right there. And then simply take that resultant and flip it around. Oh, that's not the one I wanted. It's not the blue. All right? That becomes equilibrium. And last semester, someone pointed this out, and I never thought of it before, but I think it's excellent, so I'm going to show it to you guys. Note that this can also be viewed as an example of vector subtraction. If you want to say the net force is 0, and you've got vectors A, B, and we'll call it E, right? Then the E, the equilibrium, is equal to 0 minus A minus B, right? So it's a way of showing vector subtraction as well, if you want to look at it that way. So you can either add them together, find your resultant, and flip it, or you can do vector subtraction. Those are sort of the two ways to look at it. 168 Newton sine. So what they've done is they've already taken mass times gravity. 168 Newton sine is supported in a motionless position by two ropes that each make 22.5 degree angles with the horizontal. What is the tension in the ropes? Oh? Okay. 168 newtons. Okay. Well, not the first guys. How about you guys try this one? It's almost exactly the same. We'll try this one together, or you guys try it, and then I'll show you the answer. So it's more or less exactly the same question. We still got 168 newtons. That's the same sign, right? So 168 newtons. Do we need to do both triangles drawn in? No, I'll just call that one T, and this will be TY, I guess, right? So you already know that TY, because there's two of them, it's going to be 168 divided by 2, which is that 84. Opposite sign again. Sine theta is opposite over hypotenuse. Sine 42, the opposite is what we're trying to find. TY, no, I know TY, don't I? TY is the 84. We're solving for T. So T is equal to 84 over sine 42. Someone help me out. What is it? 125? Okay, 125.5. How does that compare to before? It is considerably smaller. Well, that makes sense because the angle is more vertical, right? The more straight up and down it gets, the less tension there is. Right? Want to try this one? Try this one. Actually, all right.
Sorry, I don't know any parents.
8 Newton weight. Oh, I don't know.
It won't matter.
Doesn't matter.
Unless
8 Newton weight has one. Let me finish, you guys. There's not a lot of time. Has one horizontal rope exerting a force of 6 newtons. What are the magnitude and direction of the resultant force? What force, magnitude, and direction is needed to put the weight in equilibrium? So the equilibrium is going to be like that, right? So your first step is to find the resultant, right? So I'm going to add 8 and 6. That's going to be called my R, right? R squared is equal to 8 squared plus 6 squared. I can do that in my head. I know it's a 3, 4, 5 triangle, so that's going to be, I think it's 10, am I right? Yeah. Okay. So if it's 10, then that means that the equilibrium would be, we'll say minus 10. It says magnitude and direction. I guess if you want to assume that this is south and this is east, you could go and you could find that angle if you want it, but it really isn't one of those kind of questions. I'm happy with just minus 10. It does ask for the direction. So I guess you would have to go theta equals inverse 10, opposite over adjacent, so that would be 8 over 6. Somebody help me out. No calculator here. $52.1? 53. Okay, so I guess that would be, the resultant would be down like this. Actually, I should be finding not. I found the wrong angle there, didn't I? Right. But if the R is that way, then that means whoops. That means then that the equilibrium is this way. So that is that angle. So I guess you could say it would be west 53 north would be the equilibrium, right? But yeah, I should have found this angle up here. Okay, this is kind of the same thing, except what? They're not at right angles to each other, so you're going to have to use components, right? So you've got two ropes. Why is there, what is this? Oh, that's just for the angle. That's not anything. That's just there for the angle, right? So I've got this one. This is 62 newtons here. This is also 62, but there's two angles, right? So you're going to have to find, right? This is 62, 60. This is 62 with a 60. You're going to have to find those two, add them by components, right? Find the resultant, then flip it and find the equilibrium. Okay? So for tomorrow, you guys try number 3 and 4. There's some more problems here as well. That's kind of really it. That's the main idea. Really, I just need to give you some time to practice on equilibrium. Okay, so you've got some few problems there to work on tonight. I'll give you some more tomorrow, and then we'll have a discussion as to when we're going to have this test.